Sound is a wave of oscillating high and low pressures. These pressures are normally caused by a vibration in the air. This could be caused by the vibrations in the metal rod or the vibrations in your vocal cords. Sound waves can have a varying degree of frequencies. These frequencies determine the pitch of the sound, whether it be a low pitch with a low frequency or a high pitch with a high frequency, and also determine the notes on the musical scale. Generally, soft materials have very good acoustical properties for absorbing sounds, whether it be high and low frequencies, and hard materials, for the most part, will reflect most of the sound, allowing for a reverb or a echo. When a sound wave traveling through a medium comes in contact with a new medium, the wave is transmitted, reflected, and absorbed, the amount of which is dependent upon the characteristics of the material or the new medium. These characteristics could be that where the object absorbs much more of the sound than it transmits, allowing a room to stay quiet and keep the inside noise in and the outside noise out. This could be useful in a lawyer's office or somewhere where privacy is needed. Many walls have properties allowing them to absorb and transmit sound waves through them. Generally, the lower frequency sound waves will pass through and be transmitted through the wall, and the higher frequencies will be absorbed or reflected off the wall.
This is our cross-sectional model of a concert hall. What we're dealing with here is environmental acoustics, which is keeping the exterior noises out and the interior noises in. Those black lines there represent our sound waves. The red dots are any acoustical areas where the sound bounces off of. The green surfaces represent any area with acoustical values. The blue surfaces are the audience, and that's where our sound is reaching. There are no focal points / dead zones in the model. The idea is to have sound coming from every point through reverberation, so you have no high or lows, and everyone hears exactly the same. Concert hall is located within a building that also contains other performance venues, and to maintain sound properties within the hall, the framing members are covered with 3 layers of gypsum board to eliminate the penetration of any material, and shape of the wall allows for sound waves to come into contact with surfaces at different time intervals. Sound waves originally reflect from one surface to another, and then their second reflection scatters to become a part of the room's reverberance. There are convex panels which are affixed to the ceiling suspended above the stage, that are positioned at relative angles to the audience to channel the direct sound equally amongst the area of seating panel. The panels are made of thick plaster that is stiff and heavy enough to diminish panel vibration, and are also covered with insulation board and fabric. The same application is applied to the ceiling. Seating contributes to the absorption and diffusion of wavelengths with upholstery on the cushion and backrest, as well as the rear of the seat back with breathable woven fabric stretched over a thick, breathable open cell foam bed. The element we focused on when constructing a massing model of the concert hall is the spatial organization, which establishes the point of projection, the direction and frequency of the sound waves, and the receiving point where both direct and reverberant sound waves come into contact with the audience. Most commonly, concert halls are constructed using ordinary materials that are manipulated and finished in special ways. The floors of the stage and the hall are finished with wood paneling and backing with solid plaster members to reduce low frequency absorption through panel vibration. The walls are constructed of solid wood members that produce the same outcome as wood paneling, but are simple to install. However, the side and upper back portions of the walls are treated with an absorptive semi-rigid insulation board that is covered with a breathable fabric that controls the trajectory and echoes of some foci from the rear walls and stage. The positioning and combination of materials, shapes, and layout provides proper sound distribution, diffusion, envelopment, intimacy, and the correct reverberation times that create a pleasant and effective ambience.
For the demonstration, we are showing how sound waves travel through an open-air column. We chose to show this because it demonstrates how sound can be deadened or amplified. This knowledge can be used in buildings to control the level of noise. For example, in an office hallway, the doors to the office can be placed where there are deadening zones. This will reduce the amount of noise entering the office. We calculated the wavelengths of 3 notes. The notes are C, 523.3 Hz, A, 440 Hz, and E, 329.6 Hz. We used the frequency to calculate the wavelengths. The formula we used is frequency equals nodal points times the velocity of sound, divided by 2 times the length of the tube plus 0.8 times the diameter. The velocity of sound at room temperature is about 343 meters per second, and the diameter of the tube is 0.051 meters.
For our demo, we used these three notes: E, the lowest of the notes, A, and C. Together they comprise a C major chord in fifth root position. We used the three tubes, the shortest of them, A and C. This one deadens. The middle length tube, which uses E and C. This one also deadens. And the longest of the tubes, which also uses A and C, is meant to amplify the sound.